Okay, so let's do a quick summary of the contents of week. So, the topics for this particular week. Give me a second. Okay, so we have Bellman equations. We have Bellman optimality equations. Then we have to solve the MDP. It's called dynamic programming. The overall approach is called dynamic programming. Specifically, we look at one dynamic programming approach called policy iteration. Okay, so these are the 4 topics that are covered in this week. Now, what we'll do is we look at what the Bellman equations are. So what are the Bellman equations? You have a Markov decision process MDP, and you want to look at the value function, right? The value function is the most important quantity here. So what is the value function exactly? The value function is p pi of s equal to the expected return, right, starting from the state s, right, and then following the policy phi. So this is the value function in status corresponding to the policy phi. So if you follow the policy phi, then what is the value that you will get? The value is nothing but the expected return. So what is gt? Gt is nothing but rt plus 1 plus gamma rt plus 2 plus gamma square rt plus 3 and so on and so forth, right? So this is gt. Now, how can we write this? We can now take gamma out. This will become rt plus 2 plus gamma rt plus 3 and so on, right? So this is what it will turn into. Now, what is this expression inside this bracket? It's nothing but the return at time t plus 1. Hey Jaidev, hi.
Hi, Karthik.
So what I was doing is I was just recording something so that I can upload it at least, even though no one is there.
Yeah. I just was about to interrupt you and ask why. Like,
Yeah,
I
yeah.
thought I got some wrong link or something.
No. You're there at the right spot. So I mean, there should be something that goes into the YouTube playlist, right? So
Hmm.
I didn't want to just leave it empty.
Sure. Please carry on. I'll be here.
Yeah, sure. So I was just talking about this element equations and how we derive them. So you can feel free to drop off, right, whenever you want. So I'll just uh, record this and upload this later.
I think I'll stick around. I'll listen because week 3 content I haven't actually gone through. But nevertheless, like the math, as long as it makes sense, I'll stay.
Okay. Right. So
Please
what?
carry on.
Yeah. So what I was talking about earlier was we are finding the value for status, right? So the value for the status is the expectation of the return starting from the state and following the policy phi. So you can
So
know,
G sub T would be the entire reward of the total reward of that trajectory, right?
yeah, the total the return, right? So the sum of the discounted sum of rewards.
Discount being gamma.
Yeah, the discount factor being gamma.
Hmm.
So ideally, if you don't have gamma, then the return will just be rt plus 1 plus rt plus 2 and so on.
Hmm.
But since we are discounting it, we'll have one gamma in front of. I mean, it will first gamma square.
The geometric relationship is well established. One question I had about this is that
Yeah.
um, how do we know, or is there any specific reason for assuming that the discount will compound over time? In the sense that this relationship has to be a geometric one. Is there a good reason for assuming this, or like instead of gamma up to the power 1 to the power 2 and so on, maybe some other function of it?
Okay, so I think I'm also not too certain about this, but I think one reason is we want to make sure that the return is bounded.
It's
even for-
convergent.
Yeah. So it converges to some finite value for infinite, for continuing tasks, right? Which are not episodic and finite.
Not episodic.
Right? So that is one reason. I'm not sure if that is the.
Not that there is anything obviously incorrect or like it's not like there is something specifically unreasonable about this. It's just that I mean it seems to be like a very specific choice that they've made.
Right.
And okay, fair. And we want to keep the sum bounded. That's why.
Yeah, that is one reason. I'm not sure if you can have something other than this gamma square, some other function. I personally don't know, right? Maybe there is, but I'm not aware of it.
I'm sure there must be many ways of making it bounded, which is not a geometric series, no? Or does
Right.
that?
Yeah.
I mean, I would assume that there is, but I can't think of one right now.
Right. Yes. I am also not too sure about that. Okay, so that is one thing.
So this is, let me see if I get this right. Given that you are currently at state small s, what is the overall return you will get following policy pi?
Yeah, exactly. Yeah.
Got it.
So this is the return that you will get. So what we now do is we make use of this recursive relationship that is there, right? So we take this gamma out, factor of gamma out. So what that turns into is the return starting, whatever is there inside the bracket is the return starting from time step t plus 1, right? This is
t plus 1, yeah.
Right. So this becomes g t plus 1. So this becomes g plus 1. So we have the value of status following policy pi as expected immediate reward plus gamma times the return starting from the next state. So this is what we have now. Now what we do is just an aligned environment so that I can add into this. So now we start expanding the expectation. So the first thing that we do is the agent is at status. Now it takes an action A according to policy pi, right? So the probability that it takes a particular action given this policy is pi of A given S, right? So this is the probability of choosing an action A. Now,
given state.
Yes.
Is that? Oh, I see. So your whole okay. No, you're right. So basically, policy is nothing but this probability.
Right. Yeah. The probability of picking an action A from the status.
Given a state S, and because it is a Markov decision process, your actions won't depend on anything except the current state.
Right.
Got it.
Right. So this is the probability of picking one action A. Now, and then you have to, once you pick an action A, you transition to some other state S prime, right? A new state S prime, and along with that, you get a reward R. So this thing is jointly distributed given the current state action pair.
So the probability of transitioning to state A multiplied by probability that you're transitioning to state S prime and whatever reward you get, given that you're currently S comma.
Right. So this is all for one step, right? So it is all for one step.
For one step, okay.
And at this step, so since we are interested in the expectation, so this is the quantity whose expectation we want. So we have the reward R here plus gamma times. Now this is where what we do is now we of course have to do the second step, third step, fourth step, and so on, right? So we have to unroll. Ideally, we have to unroll the entire expectation under this policy pi. But what we do is you have taken one step and now you take the expectation inside. Right? So in some sense, you take the expectation inside and say that after one step, you get an immediate reward of R, and then you again
Gamma t plus 1.
right. So you again follow this policy phi. So that is nothing but expectation of this dt plus 1 will be nothing but v pi of s prime.
Okay, I am a bit lost here, but I'll take your word for the fact that the right hand side of the first line and what you've written in the bottom line is the same thing.
Right. Yeah. So this is for one action next state reward, right? So we have to now sum the whole thing over all possible actions because it's the expectation, and we have to sum this over all possible next state and rewards.
All possible from the acha, so it's okay. Like the second summation is given A, correct? Okay, so it's like a summation within a summation. Makes sense. It's not a product. Okay.
Yeah. So this whole thing is actually the. So what happens if you take action A in status? This is the return that you will get, but then you have to multiply it by the probability of doing that.
Going to each other state given this action. Yeah. Sorry. So basically, okay. What I was thinking is that summation over A of pi of A given S is a different term, and this is a different term. It's not like that. I mean, it's not the product of the two terms. It's basically pi of A given S multiplied by a summation and then sum that.
Right.
Yeah. Got it.
Okay, so this is the this is what we call the Bellman equations, right? So this is what is called the Bellman equations for the value function, right? So this is a system of linear equations. You notice you look at a finite MDP which has, let's say, cap n states, right? Then this will be n linear equations. Okay, so you can solve these linear equations and get hold of the value function for a particular policy pi.
Got it. Yeah.
Okay, so this is the first thing that we do in this week. We also look at the action value function. Right? So the action value function is defined as Q. Q is what we use. So
Q sub pi of A, right? Oh, S of A. Yeah.
S of A, right? So this is what happens if you are in status, take an action A and then follow policy, right? So
Oh, right. This is like you execute a step and then.
Right. So here, yeah, exactly. Right. So here, what we did was right from the start state S, or right from the state S, you behave according to policy pi. So here, what you do is you fix the action A that you will take in that state S, and then after that, you behave according to pi.
Why is it necessary to draw that distinction?
Okay, so this action value function will become very useful when we actually look at learning methods, right? So see, all these methods are just when you have the complete model of the environment specific. So when you have the probabilities known, right, the transition probabilities are exactly known, then it really doesn't matter. But in the absence of that knowledge, you need to finally decide what action to choose in what state, right? I mean, that's the ultimate goal, right? So we need to learn, the agent needs to learn what action to pick given any state.
Correct, but then that it's not clear why that is not being captured in the first one, because I think I can write Q pi in terms of V pi.
Correct. Yeah, you are
With
right.
a little bit of jugglery, I should be able to do that. So what is, I know in a physical scenario, like let's talk about some game or something maybe. What is a good example where there is a qualitatively a difference between following a policy pi and between making my first move and then following policy pi?
Okay, so yeah, if you look at that scenario, right? I mean, there is no difference. The difference as far as evaluating the policy pi, maybe there's no difference. But when you want to know how to behave optimally, right? Assume that you are in a state S and there are like 4 actions possible. Now the question arises: which action should I choose so that I can maximize my expected return.
I
Okay.
see. So it seems like we want to do it. It's a bit like doing it by induction, in the sense that if I always leave my first step off, and I know that, okay, at the end of that first step, whatever I end up in, there might be multiple policies. So I'm free to choose other policies at the next step also. Is that why we also do this?
See,
Like then we can inductively keep on solving and changing policies, right?
yeah, you can keep on improving policies.
Hmm.
So that is there. But see, the reason you define the action value function is so okay, let's forget the fact that you have access to this P, right? This P is the model of the environment, right? So you completely capture what the environment is using these the transition probabilities and the reward distribution, right? So that is
Rewards, yeah.
completely captured using Pi. Now, in a real learning scenario, this P is not going to be available to you.
Right. I'll have to learn it.
You'll have to learn. So what you do is either you learn P, you learn a model of the environment, or you find out what is the expected return. You try to approximate this action value function by choosing different actions in different states, right? So this gives if you know only V pi of s without knowledge of P, you can't estimate Q pi of s, right? S comma I.
Okay.
Okay, so let's look at this question, right? If you want to behave optimally from every possible state, what do you have to look for? I mean, like,
so discounted rewards till the end.
That is right, right? So, but if you want to decide which action to choose from a state S, so assume that there are 4 actions in a state. Now,
okay, I get it. Yes, okay.
Right? So just using the value function, you can't decide about the actions.
Got it. Because even if I know that, if I know the gamma t plus 1 or RT plus gamma t plus 1, that's just a scalar. It doesn't tell me what to do. But if I have an A plus, like some reward given A, and then I have that extra scalar, then I can change A and figure out how the whole thing changes.
Right.
So that's actually what I meant by that earlier, by solving this inductively, in the sense that it always allows me to, this is something that allows me to defer computation by one step and thereby pick the right action.
Right. Yeah.
Got it.
Okay. So this is the state value function. Now this is the action value function. So the action value function is again, so you have already taken action A in state S. So there is no probability. The policy doesn't come right away, right? In the sigma A pi A given S is not going to be there. So what we are going to have, however, is given that you have taken action A, the rest of the thing follows, right? You will go to S prime, you will see a reward R. So the probability of that happening is this, and the immediate reward that you get is R. And assuming that you
plus
behave
gamma times,
the same thing, right? So assuming that you behave according to policy pi, this thing will carry.
Okay. So that this is how we can then merge the two equations also. Got it.
Exactly. Yeah. Right. So this is how we merge. Let's
this summed over all of the that's literally what you wrote. Okay, it just clicked. Okay, got it.
Right. So this is so now you can write, as you said, V pi in terms of Q pi.
Yeah.
Right. So you have Q pi of S comma A. This is for one action. Now the probability of taking
sum it over A, and then probably the policy. Yeah.
Policy, right? So this is the relationship.
Makes sense.
Okay, so these are the.
Then wait a second. If that is so, and I have already taken. Got it. It's not like you have taken an action. It's not like t plus 1. It's like A is your independent variable there. So makes sense.
Right. Exactly. Yeah. Okay, so these are the Bellman equations, a system of linear equations. Now, interestingly, this has a solution, right? So if you can actually solve for.
What are we solving for?
We are solving for V pi of S, right? So the value function for the policy is, so V pi of S is the variable here, right? Everything else is known. So the policy pi is known.
and we want to evaluate this. That is, v pi of s should some scalar value I should get out of it, right?
Right, exactly. Yeah.
Okay.
Okay, so we can actually solve for this, and it turns out that this system of equations always has a solution. Right, it has a unique solution. Now there are some proofs for this which I am not aware of, but they are quite interesting, and Professor Ravindran has done it in his NPTEL RL course. Okay,
so the system is always solvable given a finite MDP.
Yeah,
Is
given a
that
finite MDP. Yes, that's
okay?
right.
Got
Right.
it.
So these are the Bellman equations. Now you have similar set of equations for Bellman optimality equations, right? So the point of, okay, so maybe before that we'll very quickly see what the idea of optimal policy is. So the idea of optimal policy is as follows, right? So you want the best value, right? So you want a policy pi that will give you the maximum value in every possible state. Right? So you want to behave, that's what it means to behave optimally. So you want to maximize this v pi of s among all policies. So your search space is, in some sense, it's the policy.
Yeah.
You call this v star of s, and this is the optimal value function for state s, and that is obtained by maximizing the value over all possible policies. And this is true for every state in S, right? For every state. So this should hold true for every state.
Although the set of policies, how do we know it's finite?
That's a good point. There is no guarantee that it's actually infinite, right? If you also bring in stochastic policies, right?
Yeah.
They are infinite, right? So if you only restrict yourself to deterministic policies, then maybe they are finite, right?
But
so
even for stochastic ones, can we discretize that set somehow, maybe? Or I'm not saying that necessarily it's unsolvable, because like even in, let's say that there is a set which is continuous and infinitely large, I can still theoretically find its critical points. I can find a minimum or a maximum, right? Analytically, I can do that. So it's not like this perhaps is not solvable. But I mean, the bigger question is like, are policies always finite? Do we always have a finite set of policies? No, right?
No, right. So you could have infinite. So moment you bring in stochastic policy, right? So I can keep on varying the probability for each action in a given state, right? So I can come up with.
Yeah, you're generating policies essentially, yeah.
Right. So, but it turns out again, thanks to some very strong theory, that this is actually solvable, and there is always a unique deterministic policy that is optimal.
Oh, wow.
Okay, so
there is a unique deterministic policy that is optimal.
Yeah, for finite MDPs, for every finite MDP, you can always find a deterministic policy that is optimal in this sense, right? So
that sounds very counterintuitive, but great.
Yeah,
I mean, good.
Right. So if you are, I mean, you might be familiar with this Banach spaces. Have you heard of Banach spaces?
I don't know what they are, but they are some metric space. Yes.
Right.
I mean, I don't know the definition.
Okay, so it's a metric space that's also complete. Okay, so it's a complete normed metric space. So it means, I think, these Cauchy sequences are convergent or something like that, right? So I am also not very sure about this, but it's a metric space equipped with some additional structure.
It's a closed space, yes.
Right. So now for that particular space, if you can define, so if you look at the v pi of s, right, you can rearrange terms and turn this into extract an operator out of it. So if you think about it, what is a value function? It's actually a vector in n-dimensional space, right? So if you have n states,
what would be the bases of that space?
Okay, I'm not sure about that. I am like really not sure about that, but it turns out that that's a Banach space.
I see. Okay.
So, and you can turn the Bellman equations. You can extract an operator called the Bellman operator.
Hmm.
Okay, and that the V pi of S, this equation can actually be written down as T pi. So T pi is that operator. T pi of
Hmm.
V equal to V. So like a fixed point of this operator.
Okay.
Okay, and this fixed point always exists. That's the claim. So
So
that's
which
the
means
claim.
V is an operator which sort of uniquely identifies a V, which means that we use this somehow to prove that V is optimal.
Yeah, so this is for existence of V pi, and we can use a similar argument, I believe, to prove that that there's a Bellman optimality. So there's a different operator for the optimal policy version, right? So this is the Bellman equations, right? So here it's T pi, there it will be some kind of say T star, a different operator.
Either Bellman equations come from reinforcement learning or Markov decision processes or like Markov models and things like that.
So I think they have been adopted by the RL community. I think they,
Because this seems like something that ought to have existed earlier, right?
right. I think so. Control theory and all these might have. That's what the very little that I know is that they have existed before.
I mean, they might, like in RL, they might have expressed it in terms of policies and rewards, but corresponding things must have probably existed elsewhere. And especially the fact that it's possible to find an optimal policy.
Right.
That's pretty
Yeah.
cool.
Okay. So
Okay.
yeah. So Professor Ravindran has done the entire derivation actually. If you're interested, you can link the video. So the whole thing is
I don't think I'll be able to digest it, but it's good to know. I'll definitely take a look. It's in
sure.
the NPTEL one, right?
Yeah. Okay.
Okay,
So
cool.
that's the optimal policy, right? So you have this is how you define what an optimal policy is. Now, this value function, the optimal value function corresponding to to optimal policy should be unique.
Hmm.
Right? So if you think about it, you cannot have two, intuitively speaking, right? You cannot have two optimal policies which give you, different value functions. Right.
Correct.
So
Correct. One of them will be a better value function, so
right.
therefore making the optimal. Okay, yeah.
Right. So the other part which we have to mention is you have kind of a weak ordering among policies. So we say that policy pi 1 is less than or equal to pi 2, the following thing happens, right? So when do we say this? We say this when v pi of v pi
By
1
one.
of s, right? It's less than or equal to v pi 2 of s for all states, right? So this should hold for all states. So if that happens, then we have a loose or weak ordering over the policies. So we say
Wait,
pi 2.
what do you mean by weak ordering? This, I mean, what does that mean?
So I believe it means that so given any two policies, you can't compare them, right? So let me see. I'm also not exactly sure. I should be a proper definition.
Weak ordering, it intuitive notion of ranking of a set. So basically, this means that if you remove it's because you're saying less than equal to. If you say strictly less than, then it's strong ordering.
Okay.
It seems like that is the case. Can you open the link and clarify it?
Yeah. So okay, maybe the better term is partial ordering. Is there anything called partial ordering? I don't know. So is there anything?
Such that for certain pairs of elements, one precedes the others. Okay.
Okay, not every pair of elements.
Not every can be compared.
Yeah, so maybe a better term for this is partial ordering. So this is any two policies cannot be compared. So if it so happens that the value function of one is less than or equal to the value function of the other for every state S, then you can say that pi 1 is less than or equal to pi 2. If not, you can't compare two policies.
But I should be able to evaluate any policy on any state, no?
Right, you will be able to evaluate, but you won't be able to make policy judgments. Like, I mean, judgments about which policy is better than the other.
No, what I meant is that for any policies, any pair of policies, pi1 and pi2, I'll always be able to compute the v pi1 of s and v pi2 of s.
That is
Correct?
true. That is true. Yeah.
So then what's the problem?
Yeah, but it may so happen that for pi1, pi1 of s is less than or equal to v pi2 of s for all states but one, right? Except for one state, v pi1 of s is less than or equal
Oh,
to.
I see. Okay. Okay. Like, yeah, we have to keep in mind that there are multiple states, and this inequality should hold for all states, and only then we'll say that, okay, weakly better than pi2 is weakly better than pi1.
Right.
Okay, fair enough.
Right. So, yeah. So here it turns out that according to this, we have a pi star, as we call it. We have a pi star that is greater than or equal to all possible pi's, right? So there is a pi star, it's always guaranteed, and in fact that pi star is going to be deterministic for finite MD. So that is the claim. Okay, so you could have stochastic optimal policies as well, right? So the optimal policy is not unique, but the optimal value function.
But a deterministic one will always exist.
It will always exist. Yeah, that is what the theory says.
Which means that anything that I can model as a finite MDP is learnable.
Yeah. So
an agent can learn it. That is.
Yeah, if you have access to the model, then you can actually compute this optimal policy. If you don't have access, then you can learn.
Got
right.
it.
So see, there is this small distinction. I'm also kind of picking this up now. Sir actually mentions that these are actually not learning methods, right? Whatever we are looking at now, the whole idea of an MDP and how to solve this MDP using methods where you have access to the environment model, these are not typically learning, right? So what you're actually doing is you're not using experience to, I mean, in the machine learning sense, you're not learning because there's no data actually.
I know, learning in the sense of estimation only and optimization. Yeah.
Got it. Right? Yeah, in that sense, yeah. Okay,
this seems to be like one of the fundamental results in RL, is it? Like we have perceptron separability in ML.
Yeah,
this seems to be like the motivating thing, like because you can do this, therefore we are free to do other things.
Right.
Got it.
Okay, so that is the Bellman equations and then the idea of optimality. Now, using this, what we do is we can come up with a set of equations for the optimal value function. Again, these are all intuitive arguments, not very rigorous, right? So we can ask, what is V star of S going to be? So if I start from state S and behave optimally, what is the expected return? So one way of expressing this is look at the action value function. This is where the action value. So you can define the action value function also in a similar manner. So if you have the action value function, if you have access to it, then V star of S is that action which will give me maximum return once I behave according to it and then behave optimally.
But
can we say that it is local exploration at this point? Like,
so see, this Q star of S comma A is the optimal action value function, right? So if I am in state S, take action A and then behave optimally, this is the expected return. Okay. If I am in state S, take the action A, the specific action A, and then afterwards behave optimally, this is the return I get. Now what we are saying is, what action should you choose in state S so that you will behave optimally right from now? You will choose that action which will have the maximum Q value, right?
Greedy in a way, like maximum for that state.
Maximum for that state. Of course, this should hold good for all S, right? So we can add that, right? So this is not a rigorous argument at all, right? I'm not making just making a very.
This Q star has already accounted for all the possible policies, is it?
Yeah, Q star is the optimal action value function, so it has accounted for. So maybe write that down. Q star of S comma A will be a similar thing, right? So of
Yeah.
maximizing over this, you are
Yes.
maximizing,
Yeah.
right? So
Got it. Got it. Yeah.
I mean, I am also not like 100% convinced by this particular argument. That so I always get this question. So you're making a local decision, right? So in status,
Mhm.
you're taking the best action, but of course you could start thinking about what happens
Already.
if you encounter the status in the future. So I guess that will be taken care of by Q star in some sense.
You're changing the order of the max operator, right?
Where there? Which one?
So look at the two expressions we have for V star of S. One is maximizing over pi, the other is maximizing over A.
Hmm.
Like the one thing that is not super clear is whether we can do that. And like, of course, Q star has a maximizing over pi inside it.
Right.
But like, is max an operator that is, I don't know, is it commutative? Is that the correct property? Which can be, yeah, it is, right? Because what you're maximizing is V
Okay,
pi
assume that you have
for Q star.
computed. So yeah, if you look at it that way, I'm also a bit confused actually, to be honest. But if you look at it this way, where you assume that somehow you have estimated the Q star function, right?
No, it actually, it makes sense. I'm just trying to see whether that, it's symmetrical or not. It's like saying, two integral signs and you switch them
Okay, okay.
and it doesn't matter. But, integrals are not clearly not the same thing as maximizing something. So maybe when
Right.
you're maximizing, it doesn't matter. And yeah, that makes sense. Whether I maximize over rows or columns, it doesn't matter. As long as I get one maximum value out. It could be that.
Mm.
Maybe V star of S will be summation of all Q star given A state. I mean, all the actions within a state.
Sorry, can you come again?
No, given V star of S will be a summation of Q star of S given A state. I mean, considering all the actions in a state.
Uh, B star of S, it won't be a summation. It will be more of picking the best possible action I can.
Yeah, no. Let's say V star is a expectation, right? V star of S is it.
It is an expectation.
Then given, I mean, again, Q star is a more of conditioned on action, right?
Yeah, I mean, for Q star is more of. So you're breaking down the problem into two parts, right? One is
I
forget
mean,
about the current step.
we can get one from other, right? Given we
Yes,
condition.
you can, yeah.
So, I mean, I think Max
Yeah.
might make it like on a linear approach. We are getting if we do summation on all the actions, we get V star S.
Right. So see, the only difference is okay. What I'll do is I'll go ahead and write down the corresponding equations for this. Okay, so I'll write down the optimality equations as they call it, and we will maybe that will help us a little bit more. So this part is okay, right? So I mean, roughly, maybe we may not get it 100%, but assume that this part is what it is. Now, what we do is we are going to look at Q star of S comma A. So Q star of S comma A is what the first step is clear. First step you are going to take action A in status, and the probability of doing that is going to be the same, no change there, right? So this is the probability of taking action A in status, and you will get an immediate reward of small r, right? So that part is not going to change. Now, according to the definition of Q star, you are going to behave optimally from state S prime. Okay, so if you behave optimally from state S prime, you're discounting the rewards, right? The return is discounted sum of rewards, right? So that gamma has to be added, and then you're behaving optimally. So the return from the state S prime is going to be V of S prime.
Okay.
Okay, so instead of so if you look at the difference between so this is called the Bellman optimality equation. So if you look at the V pi of S equation here and here, you see that here there is a summation over A, whereas here you have a max over A. Right? So that is one of the differences. So this is called the Bellman optimality equations. Okay, so immediately you see that this is not a linear system of equations. Here also you have n equations, n unknowns, if there are n states, but then you have, because of this max operator, you can't like easily solve for this.
Can
Even
you
though
go back to the equations?
the Bellman equations.
Yeah. I mean, all this is saying is there's bound to be one which is the maximum of all.
Right.
Oh no, but then that is the whole
Yeah,
point,
that
right?
pi will
Yeah.
change to E star. And then you will choose the maximizing action at the current time step. Right. So there are two changes. The expectation over the action A. So changes over the choosing the maximum action currently and then behaving optimally afterwards. So the pi changes to star, right? V star.
Got it. Correct. And but then how do you figure this out? Or so the equations are solvable, but the optimality is not, is it?
The
It
equations are
exists, but it's not like it's not solvable in the
Or
sense it's not
is
easy
it
to
an
find.
approximation?
okay. So how do you solve this? Is that the question?
How do you find it?
Yeah. So you have
Huh.
there are like multiple methods. So you have a class of methods called stochastic dynamic programming. So they use concepts from dynamic programming to iteratively estimate V star of S.
Okay.
Okay, so we that's the next thing that's covered in this week. So how do you actually go ahead and solve for the optimal policy? In fact, we do several things following this. Once we have defined the Bellman equations and optimality equations, first thing we study is, given a policy pi, how do we solve for V pi of S? Even though it's a system of linear equations, you can solve for it, but how do we iteratively solve for it, right? So that's the moment you have an iterative solution, it's easy to code that up, right? So we look at that, and then we take the idea forward and look at how to find an optimal value function and an optimal policy out of that. So that's the next two things that we look at.
But in order to do that, we should be able to compare policies.
Right. Yeah, exactly. Right. So we need a way to compare policies. Even better would be a method that will help us get a better policy once you are given a specific policy. Right. So if you are given a policy pi, if you can find out or if you can construct a pi prime that is better than pi, then you are
better
that will be even more better, right? So that is the next thing. So what we have is called the policy improvement theorem. Again, we don't prove the theorem; we just state it without proof. So this is what the policy improvement theorem states, right? So if you have a policy pi, any policy pi, doesn't matter. So let's take any random policy pi. You can always construct a policy pi prime that is better than this pi. Okay. So how do we? What is that better policy going to be? So this is what is the claim
the
again.
V pi of S will be less than or equal to V pi prime of S, is it?
Yeah. Right. So okay, let me write that down. So V pi of S. So we are looking for a policy that satisfies this V pi prime of S, right? So I have this shortcut. Sometimes they work, sometimes they don't. So
What is this you're using?
And this is called MathCha, mathcha.io. So
okay,
mathcha.io.
Policy improvement theorem says that pi and pi prime will always exist such that this is true.
What it says is, given any pi, so any pi, you can always find a pi prime such that V pi of S is less than or equal to V pi prime of S. So that's actually not the theorem. The theorem is that it actually gives you a way to find this policy. It says that if you are greedy with respect to the value function of pi, then the corresponding policy will be better than pi. So that policy is pi prime.
Sorry, could you repeat that? If you're greedy with respect to
the value function of pi, right? So let's look at it this way. No, so Okay, so we have v pi of s. Let's forget about the inequality for now. Now we have v pi of s. Let's
Right.
look at corresponding action value function, right? So like fix s here. Now for v pi of s, you have, let's say, some k different actions, a1 to ak. So yeah, you can compute q pi of s comma a, right? So now what we are claiming is, assume for a moment that pi is deterministic, right? So meaning you can only take one action from every possible state. Of course, you could take different actions from different states, but then you can take only one action. It's not stochastic. So can I write v pi of s as q pi of s comma something in that case? If oops, sorry, number went out of my, yeah. So let me come back to this. So did you get the question? If I want to write v pi of s in terms of q pi of s comma something, when pi is deterministic, what should I plug in here?
Pi is deterministic. Just S. There's nothing, because you'll always take only one action, right?
Right. So what will that action a be? So a will be equal to something, right? Can I write that in terms of pi? So
Yeah, pi of A given S.
right.
Or
So
pi of
it's
A
actually,
rather.
so since you have only
Pi
one
of S, yeah.
pi of s, right? So this is
Correct. There is no
equality,
given A or anything, given A given S, because it's deterministic. Yeah.
right? So now that you have this particular statement, what you do is, if I act according to policy pi, this is the value that I get. Now, what if I end up choosing an action A that gives me a better value starting from status? Okay, this action A will exist, right? For sure. It'll at least be greater than or equal to the q pi starting from S, right? And following pi of S. There should be one action at least.
Why? Acha, well, equality also holds. So,
Equality,
yes.
right?
Correct.
So instead of choosing any random action, what we do is we choose the best possible action starting from status and taking that action and then following policy pi. Right? So I can do, right?
S given A overall A. Yes. Yes.
Right? So this will always hold. So now what the theorem says is that, what it claims is that, if you set pi prime of S to be not simple max, but an argmax over A of q pi of S comma A. If you, this is your policy. This is, you do this for all S and S, right? So do this for all possible, every state rather, right? So you do this for every state. You choose that action starting from status, which will give you the maximum value for the current policy. That particular action, you set that as pi prime of S, then leads to the following: pi prime greater than or equal to, greater than or equal to pi. Is what the claim is. Okay, so if you're greedy with respect to the value function of the current policy, this is the value.
So the greedy part is that argmax.
Yeah.
Okay.
Right? So this is often called the greedification step. If when you look at algorithms to solve for the MDP, so this is the greedification step where you behave greedily according to the current value function or the value function of the current policy. That will surely give you a better policy.
Or the same.
Or the same, yeah. So interesting thing is, if you end up with the same policy, okay, that's a good place to stop, right?
Which means you have, you're at the local optimum anyway.
Yeah, so you would have reached the optimality, right? So you would have. So if you notice, this is max over a q star of s comma a is equal to v star of s. Roughly, that's what we are saying here. So if you remove the arg max and you replace this with with v of s, right? So you will end up with v of s equal to max over a q of s comma a. Roughly, you will end up with the same equation. So if you're optimal, rather if you are the new policy is only as good as the previous policy, that means you have reached optimality. Okay, I'm sorry, I'm not like I'm also not rigorously stating all these things. This is all I also know. So they're all more of intuitive arguments and not proving any of these things.
Now I'm a bit worried about what's going to happen in the quizzes.
Right. Okay, so that's the policy improvement theorem, and so far we have looked at the Bellman equations, Bellman optimality equations, the notion of optimal policy, and policy improvement theorem. So the final part of this week is discussing how to solve MDPs.
I guess that is where like a lot of these things will become very, very clear.
Right, yeah. Okay. So do we go over that or shall we go over that part also? Or do
Yeah,
you
yeah,
want-
absolutely. I mean,
Okay. Okay, so the
anyway, I'm sure Karthik, you might have to repeat it eventually later in some class, but since we're here,
yeah, sure. So that's called policy iteration. So policy iterations, see the algorithms thankfully are not so hard, right? So this setup is kind of, it may look hard, but then once you come to the algorithms that are used to solve the MDP, they're quite, they're much more intuitive than what we have seen, right? So there are two steps to policy iteration. One is called policy evaluation. Okay, the second step is policy improvement. Okay, so policy evaluation is often called the prediction problem. Is important because in the future we'll often call this prediction problem, right? So if you look at RL, there are like two things that we'll constantly be talking about. One is the prediction problem, the other one is control, right? So prediction is given a policy pi, what is the value function, right? That is the prediction problem. Control is how do I behave optimally. So what control is all about, finding the optimal policy. Okay, so
I
policy
see.
evaluation, right? So that is the terminology will follow. So if you look at week 5, week 6, we'll suddenly switch to terms like
For a minute, I thought that these are the two types of RL problems that we are interested in: prediction problem and controlling something problem.
the final goal is to control, right? But prediction is useful in helping us achieve that goal, right? So policy iteration is a classic example of that. So this is the rough idea, right? So you start with some arbitrary policy, right? Start with some arbitrary policy pi naught, and then what you do is you evaluate that policy, so you get v pi naught. This you can do, right? So you already know you can do this by solving the system of equations, but we look at an iterative approach. That's what policy evaluation is about. Once you evaluate the policy, you can be greedy with respect to the value function of that policy. Okay, that is going to give you pi 1, which is strictly better than pi naught, right? If it is not optimal, we know for sure that pi 1 is going to be better than pi naught, right? By policy improvement theorem. That's where the whole policy improvement theorem comes, right? So given a policy, how do you come up with a better policy? So once you get pi 1, you repeat the whole procedure, right? So you compute v pi 1, evaluate rather v pi 1, then be greedy with respect to that, go to pi 2. So you'll keep doing this. And it turns out that here also you are guaranteed to converge to pi star, right? If you follow this procedure, you will certainly reach the optimal policy for finite MDPs. Okay, so that's the overall idea of policy iteration. So policy improvement, you already know. Policy evaluation is actually quite simple. So you take the Bellman equations, right? You take take the Bellman equations and turn it into an update rule. So this is the Bellman equation, V pi in terms of other V pi's, right? So what you do is start with some random value for V pi. So on the right hand side, let's say you have Vk, right? So Vk. On the left hand side, you turn this into Vk plus 1. So it's an iterative procedure to evaluate the policy pi. So does this make sense?
Kind of. Actually, it will be. I'm sure this is probably going to come up. But if you like saw an example of this whole discussion, which may be like a simple game like tic-tac-toe or something.
Right. Yeah. So in fact, I am.
Which is very finite and it's easy to interpret and so on.
Right. So yeah, I'll try to. I'm actually working on tutorial for that. So one on policy iteration and one on the next algorithm, which on a small grid world. Right. So I hope that will be of some use.
In fact, the two MDP examples that you have given in the last week, even if we did on them, in fact, that would be better because it will be some continuation there because we are already aware of those MDPs.
Right.
So if you could learn an optimal policy for the haunted house or the other one, the robot.
Yeah. Sure. So we'll work on that. So this is the basic idea of policy iteration. If you start with some value of V pi, so typically you start with zeros all through, and then you keep doing this for sufficient number of iterations. Eventually, you will converge to V pi of S. Right. So this is policy evaluation. Nothing fancy about this, but yeah. So that's all there for this week. So this is one example of a dynamic programming based approach. Now there are other approaches. So there's one algorithm called value iteration, which we'll look at in week 4. Okay, so that's all I had basically. For any other questions or anything else you would like to discuss?
How much of programming? I'm sure a fair amount, but like, could you maybe throw some light on?
So we have 3 programming.
What kind of coding we are going to end up doing?
Yeah, so we have 3 programming assignments. One. So
it'll be all Python, right?
It'll all be Python, basic Python. You won't even have to use
libraries and stuff.
Libraries, right? If you want, you can. So there will be 2 on classical RL, whatever we see now, and there'll be 1 on deep reinforcement learning, right? Where we'll use some deep networks, but they won't be deep in the sense of like several layers, nothing of that kind. But still, they will involve neural networks. So that will be the 3rd assignment. This first 2 will involve whatever we have studied so far. So actually, the first one is due. We have to release one this week, and we'll try to release it by the end of this week. So the idea is to make them coincide with the exams, right? So first 4 weeks programming assignment 1, at the end of 8th week programming assignment 2, and then roughly around end term exam, the last one.
Could you tell us a bit about where do neural networks even come in over here? Because it's not like we are solving vision or NLP problems over here, right?
Yeah. So
or I don't know. I mean, there could be instances where people have used reinforcement learning with deep learning to solve some vision problem, let's say. So where, like, not even in terms of say the course or something, but when people say deep reinforcement learning, and now that we have like some idea of the full RL problem, okay?
Right.
Where does deep learning come in?
Okay, so again, limited understanding at the current stage, right? I am also like not entirely sure, but this much I know. So you have, these are all called tabular solution methods, right? Or tabular methods. You look at the textbook, the author calls.
Yeah.
So meaning you have your states can be represented in nice.
The MDP can be represented as a table, is what they mean.
Right.
Hmm.
So what will happen is when you come to real world problems, let's say for example Atari games, right? When you're playing Atari games, now
Oh, okay, got it. Yeah.
you can't represent the states, right? So
Hmm.
one uses use a neural network to represent the value function itself, right? So you have maybe a small CNN, and the image, the raw pixels are themselves passed into.
States. Yeah.
So the neural network there is going to be used as a function approximator. So it's like
Oh, I see. So if I'm playing on a 10 by 10 grid of, I don't know what that game is called, the bouncing ball game.
Yeah, I'm
Now,
not
my ball is moving diagonally, and it moves right by 1 pixel and up by 1 pixel, let's say. That's technically speaking, from a tabular perspective, it's a different state entirely.
Right.
But I'll need a CNN to discretize that into a smaller set of states. Is that what you mean?
Yeah. So some
Got it.
representation of the state, and if I'm not wrong, the it's used as an approximation for the value function itself, right? So S is going to be bunch of say 256 cross 256 image, and then V pi of S is going to be or maybe Q pi of S comma A is going to be the last layer softmax over whatever, or maybe just
Right.
something like that, right?
Oh, I see. So it's not just state parsing or interpretation or anything like that. I can actually use neural networks for approximating policies and values themselves.
Right.
Got it. And both. I mean, you can apply networks with both areas. Yes, got it.
Yeah, so that's what we'll do next. So even in these 2 weeks, right? So there are some questions. For example, this week there is a question which requires you to, if you write code for it, life will be easier. So for solving this, so that might be an interesting thing to do, right? So it may help you for when you actually come to the later weeks. But that's one thing you could try doing. All right. So anything else? So if you want to discuss the practice assignment, or shall we'll release the solutions and you can maybe go through that? Did that work?
I think there is enough time for that, thankfully. So
okay. So shall we just we'll just release the solution? That will work, right?
you mean you're planning to do it before the deadline, is it?
Yeah. We can release it, say tomorrow or whenever you guys want it. The question is, do you want me to go through it now, or?
No, I think it will be better if you release it. Let people know that you have released. Let them go through it.
Sure.
And then discuss it, because otherwise, I'm pretty sure I will show up completely blank.
Sure. Okay.
If I haven't done my homework yet.
Yeah. So anyway, the deadline is next Sunday, right?
It is next Sunday, yes.
Okay. Week 4 we haven't even released, so we are yet to prepare questions. So we'll hopefully try to release it by Monday at least. Okay then. So anything else? If not, we can take a day. Hi Kiran, do you have anything?
No, that's clear.
Thank you. All right. So thanks Jaydev and Sai Kiran for joining. At least you saved me. Otherwise, I would have been just talking to an empty screen.
Thanks for sticking around. Even I was late by 10-15 minutes, I think.
No, I mean.
Oh, okay.
You guys at least turned up.
I was late by 30 minutes.
He was just Karthik was just talking to himself for 10 minutes, recording something. It's great.
All right. Yeah. So we'll meet again maybe next week. We'll release the solutions soon.
All right. Thank you.
All right.
Thank
Yeah.
you.
Thanks.
Bye.
Yeah. Bye.